Presentation that showcases the practical integration of machine learning into production monitoring systems. 4D Eagle S demonstrates how advanced vision and AI models can enhance hot surface inspection and quality control for long steel products, ensuring precision, consistency, and real-time responsiveness. Our next speaker is Mr. Santino Keuseman, Managing Director at Cox Measure Plus Inspect. He leads the development of innovative digital solutions for inline measurement and inspection systems, combining cutting-edge optics, machine learning, and process automation to optimize steel quality management. Mr. Santino Keuseman, it's a pleasure to have with us today. A big round of applause to him, please.
Thanks a lot for the introduction, and thanks for everybody for being here, although that it's 5 o'clock. Yeah. So I will speak a bit about quality assurance when measuring long products of hot steel and how to use machine learning to do surface inspection. On the left side, you can see our measurement gauge, the 4D Eagle S, and on the right side you'd see the gauge in front of a 3-roll rolling block system manufactured by Cox. And many of the high quality round products or hexagon products are rolled by a Cox block. And of course you still can have defects on the material. Yeah? And I will speak a bit about the technology, how we actually find things, and give you some detailed insight. So, we don't only want to see the surface, we also want to measure the round. Yeah? And if you want to measure round of long products, there's basically 2 types of laser principles in the market. The older one is the laser shadow system or principle on the left side, where you have a light source on one side and you measure just 2 points basically, or as many points as you have light sources, and then there's sometimes up to 6, but you only get a couple points around the circumference. So if you'd have a square in there, you'd get the same signal. So clearly you cannot do any kind of surface inspection with this. And also you only get a quite imprecise signal or information on the round. What we use is laser light section principle or laser light triangulation, where you scan the complete surface of the bar with 4 heads and 2 different laser colors, and then you get a topography of the surface. So you get actual 3D coordinates of each point on the surface where the laser hits the bar. And if you have that at a very high frequency, yeah, you can match a very high resolution along the rolling line, because many of our customers, they go up 20 meters a second, 25 meters a second, or even higher. So 3 years ago, we developed a system together with our partner LAP, who has been producing measurement gauges in the market for a long time. We also have more than 10 years of experience. And our goal was to have a machine that does both. Yeah, so scanning of the surface and measuring the profile, and at the same time have a nice, let's call it flexible HMI, and give also the customer all the data. Yeah, many measurement devices are closed. And we developed that and installed the first systems at Saarstahl. A little bit earlier today, there was also one speaking from Saarstahl. So this is from Saarstahl on the left side. And you can see there in the right image the 2 laser colors interfering on the bar. And we currently have 4 systems running. 2 are currently being commissioned and 2 more in the next year. So what's our general principle of operation? We first scan the complete surface of the bar and detect any type of deviation from the ideal geometric surface. Yeah? But with that, you only, you detect everything, but not everything is critical, right? So what we do is we take any deviation that we detect and feed it to a set of pre-trained neural networks. And then, based on our algorithms and also what the customer considers to be critical, we give out a warning that goes to operator and quality department. Yeah, so one aspect is, of course, the complete classification, but also for any rolling mill, it's always important to have a periodic defect detection. That's a bit behind that word smart algorithms. So we combine a Fourier analysis together with image recognition techniques of neural networks. We currently can measure from 10 to 150 millimeters and are developing the other sizes. We go up to very high frequencies, and that's the only way how we can actually achieve sizes that are below a millimeter or in that range for the defect size. Yes, the thing is, you can have every plant is basically individual. I mean, many of the defects are similar, but depending on the quality, the material the customer is rolling, it's always something different. Yeah, that's why we can actually train our neural networks on site. Yeah? And together with the periodic defect detection, we're able to find roll breakages, which would really cause problems to our customers. Additionally, we add an HMI, and all data is opened. We have an OPC UA connection, so basically all the data that our gauge is producing is also sent to the customer and transparent at every moment. At the same time, we have a multi-client support HMI. That means everyone can look onto the gauge what's currently rolled. This is for the profile measurement. We usually have two screens. One is for profile measurement, one is for surface inspection. And it's all customizable because we've noted, you know, people are always different. If you go to one plant, somebody will say, oh, I need that line in green, or I need it in red, or whatever. So everything is customizable. You can decide what numbers you see there, what sizes the graphs are to be, or colors of the measured information. Well, and in the next one, I have the surface inspection. And below you see the length of the bar is the horizontal axis, and the angle is the vertical axis. So we unfold the surface. On the top, you always have the current bar. Below, you have the last couple ones. And the size of the icons is for the depth of the defect. And you can open each defect in detail, see it in 2D and 3D. Yeah. And we have a periodic defect detection that is up there. So that determines, okay, what's the distance between the defects and how many times do they come? Because with this information, you can say, okay, it's from the roll at that stand, as an example. And the middle column shows the sum of all defects, and the left one is the top bar. So I'm explaining this because this is our data source from where we go and then put on top the machine learning. Because what the color is of the defects, that's what we pre-trained the system. So if there's if the system goes online after commissioning, and as soon as you have enough defects, we can start training, and that's how we represent the color. So it's one thing always, what does a gauge measure? The other thing is what's the reality on the bar. Yeah? And these were the images that I've just shown you, and that's what we find on the bar. So we can easily detect something around a 1/10 or 2/10 of size deviation. Here's another example. And this is actually quite a typical defect at a customer with a certain material grade, a low alloyed steel. That occurs quite often. So in this case, they were able to, I think it just took them 3 weeks, and we had more than 300 occurrences of this type of defect, and we're able to train quickly our set of neural networks. Okay. Now, defects. Yeah, these are already a bit pre-processed. That's why they're not so sharp. But if you have a gauge that detects a lot, you find, of course, lots of defects on the material. but you also find things that you don't want to find. Yeah, with any measurement device, you always have, I don't know, it's either scale or it's dirt that's flying through the gauge, or maybe some water droplets. So there's always a need to filter as well. And filtering is even more important sometimes than finding defects, because if you have, I don't know, a lot of false positives, nobody's going to look at the signal for the defects, right? But the problem is you produce a lot of data quickly. Yeah? And as an example, I've put down there the scale. Scale is also some oxidation that forms on the material. And for the surface detection, it's clearly a geometric deviation, so it's an error, but not for the customer, because the customer says, yeah, I'm going to peel it, and then it's no problem. So you have to distinguish between what is actually a defect and what not. And that means you need to classify. But the problem is, if you have a lot of data, classifying takes a long time. I mean, we basically produce a couple hundred megabytes per bar if there's a lot of defects on that. And if you have, after 2 weeks, 200 gigabytes of data, you know, it's difficult to find somebody who would go through all the images. Right? And unfortunately, trained monkeys aren't smart enough to do that either. So you have to figure out a way to do it with algorithms. And what we did and had a lot of success with is to use first an unsupervised learning approach. That means you take all the data, you roughly estimate how many classes you might have, and then you throw it into a set of pre-trained neural networks that you can that are openly available. Yeah, and you combine that with clustering algorithms, and then together you can start already to get pre-trained classes. Yeah, and then it's a lot easier, because you have then maybe 15 classes or so, and each one with a couple hundred images, and then just a human needs to look into the class and basically scroll through all the images and say, okay, this one not. Yeah, the rest is perfect. And that's then where you switch to supervised learning. Exactly. And I have picked out a few images of the material that we got. And one of the reasons, by the way, why we go for laser triangulation, not for camera systems, is because the main quality criteria for our customers is how deep is a defect. Yeah, that's most of the times the one criteria. That's why we thought, okay, we need a system that's able to detect the depth of the defect. Yeah, so we need 3D data, and that you can only achieve with laser triangulation. And also you can see that actually in those images I picked in there. The one I'll speak about is an overfilling, and the other one is a tear. That's a surface deterioration depending on the presence of, let's say, wrong alloys. Yeah? When training something and testing something, a good question is always when is a result good, right? So what we've set as our measures is the true positive rate and the false positive rate. That means the true positive rate would be how many instances of the total occurrence that happens did I identify correctly? Yeah. And on the other hand, the false positive rate, that means how many times did the system basically give a false alarm. Yeah? And we've so far used a set of to say, okay, 70% true positive rate and 1% false positive rate are the things we think most of our customers can work with. So stay below 1% of false positive rate and above 70% true positive rate. Now, as these neural networks never, let's say, they never really give you a clear yes or no, you can, of course, change these values a bit. Which we've done for the filtering, because in the top two, the overfilling and the tear, those are defects. Yeah? In the bottom table, I have two types of things that we wanted to filter, and for filtering, it's even more important to filter more. So when you increase the true positive rate, you usually also go up with a false positive rate. But for filtering, it's okay. Yeah? We think. So far, also our Our experience is it depends how much data do you need for training. Yeah, it depends how optically significant those images are. If they're very close together, it takes more images, but usually 200 to 500 is enough. And with that, I will already start with some conclusions. So we developed a system that does three-dimensional measurements based on laser triangulation, and those we use in order to do surface inspection on the geometric data. Yeah? And then we take all those information, put it into unsupervised learning to determine the initial classes. And this really speeds up all the commissioning phases, yeah? Because, of course, you can say defects are similar, but in the end, I know that it's always something different in every plant. And also, the requirements of the customer are different, yeah? And then, after we've done the unsupervised learning, we go into supervised learning for fine-tuning. And with that type of approach, it doesn't matter how many classes, basically, as long as there's enough data, of course. And we think it's very important to give out all the data, because some of our customers even have their own AI departments. Yeah? So all the data that our system is showing is also available for the customer. And with that, I would like to conclude. Thank you.
Mr. Koefsemann, thank you for sharing openly all your knowledge. We have one question for you. From your perspective, how will machine learning and optical technologies transform quality management in the steel industry over the next decade?
I think it will become standard. I think back in the old days, everybody used to try to work with, let's call it, empirical models and maybe an analytical approach. But nowadays, since we have a lot of graphic cards and a lot of machine learning, you can basically just almost solve everything with machine learning. And I think it will become standard, because everything I've heard today was also how do we control a furnace, how do we control an oven. Everything is using machine learning and big data models, and I think that will be an advantage of the steel industry in the Western world, I would say, I hope.
Thank you. And another one, the last one. What are the biggest challenges in achieving real-time responsiveness and reliability in automated quality control systems?
Yeah, delay time, of course. Huh? Delay time is always a challenge, yeah, because the complexer the systems, the more data is flowing, and as soon as there is anywhere a lack or a delay of data, you already get a problem. Our customers usually, they have a gap time of 3 to 5 seconds, so that means in between those seconds they need to send the new data, what they're currently rolling, with the specification. Yeah? If they don't, then something is not working. And especially once you go to real time, I think, yeah, that's very important.
Thank you very much, Mr. Koefsemann. A big round of applause to him, please.
Thank you.
Thank you.